everyone, to Tech and Operations. You have Spencer Morrison here and Clint Mason on the line. We had a wonderful recording session last time. If you haven't had a chance to check out our plunger lift guru, Clint Mason, who spoke last about 3 episodes ago. So we really dove into kind of the plunger selection piece. How do you know which plunger to have in the well? At what time of its life? The first year, the second, the third? Is it a fast fall? Is it a ball and sleeve? What does that look like? So we really covered some fundamental elements. What we noticed when we were going through that conversation was we're kind of missing this other fundamental element, being like liquid loading. And maybe we can touch a little bit on the vertical side and how that's more understood. But then the real problem we're facing is liquid loading in the horizontal and how misunderstood that is, and the consequences from just how liquid is behaving in a horizontal, 2-foot or 2-mile lateral. So, Clint, do you believe liquid loading is one of our most critical issues to face with plunger lift?
Yeah, I 100%. I mean, first of all, thanks very much for having me on again.
Yeah,
And
welcome back.
I enjoyed it last time. I'm hoping we can have another very interesting talk. Like I said, we seem to entertain ourselves any of these, but hopefully other people get
Yeah.
some fun out of it. But when we talk about liquid loading, and we've all been so focused on vertical. Like at least me, I'm an older guy, and I've my early years were always vertical.
Mm-hmm.
Horizontal was pretty new, probably been 10 years started, we've been messing with in the last several years. It's been very, very focused on horizontal. So the learning on how wells liquid load it's been completely new, completely
Yeah.
trying to understand that. And, when it comes down to it, you need to relearn and understand the complete well bore in a horizontal and and how every section reacts different, because we're so focused on the tubing. And the
Mm-hmm.
one thing that I find in all horizontal wells is by the time we react to the tubing, we have missed months, if not years, of liquid loading, fluid hang up, all sorts of
Mm-hmm.
issues below the tubing that have really caused a tremendous amount of the deferred production. And we miss it. Everybody misses it
Mm-hmm.
because we're so focused on tubing.
What do you mean by that? React to the tubing piece, but we're so focused on, when to react to the tubing, we've missed the downhole element. What do you mean by that?
Well, I mean, so when you talk to somebody, the first thing, a production engineer or whatever, or even us, right?
Yeah.
When you get below critical rate, which critical rate is not a line, a point. It's, in my opinion, a
Sure.
window. So you got to be,
Yeah.
I find it's about 20% higher than most people, or it's happening in the tubing. But anyways, but people are focused on critical rates. They say, well, my well flowing at this pressure, at this rate, is going to hit critical rate at
Mm-hmm.
600,000 or 500 or whatever the magic number is. And, so that they realize, okay, well, I see it at 600,000, we start seeing
Yeah.
the well liquid load or stop producing, right? You get a big fluid column in the tubing, it collapses, the well, it's easy. Let's throw a plunger in, let's do something, let's add compression, whatever it is,
Mm-hmm.
and we react to it. But
I see where you're going with that. You're saying we're paying so much attention to the fluid and gas flow in the tubing,
right,
the flow of all the liquids and gas, that we've completely forgot about that entire lateral.
that's right, because
Got it.
what's the impact of the churn area and the transitional? What's the impact of that total horizontal leg where you've got 1,000 little peaks and valleys that are constantly
Mm-hmm.
sitting, filling with fluid, right? And you're trying to, I mean, if you look at a pipe and you think about it, right, and it's
Mm-hmm.
sitting horizontal, and we know when we drill, it's not a nice smooth like hydraulic
Oh yeah,
bore, right?
that's right.
It's not toe up, toe down. It doesn't matter because it's
Yeah.
toe up and toe. I mean, there's 1,000 little bumps. Well, if you've got a 4.5 inch hole that goes
Mm-hmm.
up and down a foot, there's a lot of valleys, right? There's a lot of
Yeah.
places, and every one of those spots are a place where you're going to. First of all, the other thing is think about the horizontal section as a separator, right? If I've got
Mm-hmm.
2 miles of horizontal section, what is my total fluid capacity of in that section? Like we would hold. 100 barrels
It's a really
or
good point.
150 barrels or 200 barrels of fluid. Well, if I got a well that's producing 30 or 40 or 50 or even 100 barrels a day of fluid, and I've got 10 or 15% water, but it takes me 24 hours from the time that liquid comes into the horizontal to the time it moves to the tubing, what's going to happen? So we see this. We'll see water starts to drop out, and water will sit on the bottom. And when you look at the way, the gas is basically going across the top of that pipe, it's skimming a very thin layer of liquid on
Yeah.
top and moving it along. And as you get farther and farther into that pipe, there's really no movement. So it just kind of builds up until it gets to the point where it creates enough resistance that the gas slugs it. It has to push it,
Right, right.
right?
Hmm.
So
So we're basically stripping the light ends, the light oil first, and then probably the heavier bit of oil that's sitting on top of the water. And then so we're hitting that.
yeah,
And then you're saying by friction and by maybe a good surge, maybe you have a pressure build for a couple of days because it was shut in, good surge. Then you kind of sweep a lot of that liquid,
yeah,
but it's still just building down there in these
that's
valleys.
right. And you start this wave, and the wave carries all its way to the tubing. Now, when you look at your churn area, basically, you've got gas, you've got your liquids coming, and it starts to
Hmm.
turn to vertical. Well, as soon as you go around a corner, everything that's heavy gets pushed towards
Yep.
the wall, right to the far wall. Well, the gas is racing across the top, so your water has a tendency to run down. So you'll start getting and I mean, if the well's producing 1,000 barrels a day, I mean, it's like a fire hose, right? This isn't
Sure.
happening. It's just but when we get into optimization, we see this where we start if you got really good tracking, where you're looking at your water cut and your oil or condensate cut, you
Hmm.
actually can watch that and you can see that water cut start to drop. And there was some
Interesting.
customers we worked with where they had excellent on-site tracking. And basically, we went back and watched their water percentage of their cut, and we could see almost 24 hours before the well would liquid load and die. And the wells were flowing above tubing critical rate.
Sure.
And so they'd be flowing along really nice. And then if you were watching your water cut, you'd see that went from 8% to 5% to 3%. And then it would drop down to almost nothing. And then a couple of hours later, just boom, they would just, it's like somebody turned a tap off on, right? So then, okay, well, you're above critical rate in the tubing. Why did it
Yeah.
liquid load?
Yeah. So what happened downhole to cause that?
Right. So all of a sudden, this water that we're not lifting is sitting in that churn area, and it's building up. It's building up,
And where's that churn area
and
located?
it's basically right as you come off the horizontal and you start to
Sure.
turn. So it's but the area between it's probably about um, say 15 degrees from horizontal
Yeah.
to about 60 degrees, somewhere in
Yeah.
there.
All right. I'm
Talk
with you.
about end of tubing position of how that impacts it. Well,
Hmm.
but as it's going around there, you get this churn. So it's very hard to push fluid around anyways, but it's almost
Yeah.
impossible to push heavy fluid because it's falling underneath that coil and it's sitting
Interesting.
there and kind of laying. So instead of having a well that's coming at you with 8% water continuously, all of a sudden you build up this, you displace the oil because it's just lifting, water sitting there, it's lifting it up, and the oil
Hmm.
stuff you're bringing in is pushing up, it's getting thinner and thinner, and then all of a sudden you get this big slug of, instead of 0% water and 100%
Right.
condensate because the water's not coming up, and you hit it with 90% water. And now the
Yeah.
density of the fluid, you have no energy to push that water because the energy that's been lifting the condensate because it's lighter density.
It's easier. Your weight's so much heavier
And
now.
then
Yeah.
when it comes and enters, it's a big slug. Boom. So all of a sudden we overbalance. Or not
Sure.
overbalance, but basically we stop it from flowing. Everything in the tubing starts to collapse. We create this whole
Hmm.
uh, very quick action where liquid kind of stops moving, and then you've got to get it going again. And
Yeah.
it's what's really started kind of cluing me in was every time we went out and we had a well that we worked on where we lost it, we would pull a swab. And you'd have wells that are 10 or, like I say, low percentage water cuts. And the very first two or three swabs were almost always 100% water.
Hmm.
So why?
Hmm.
So that was kind of, well, obviously we're getting separation. So that's one of the things that we got to pay attention to. So how do you make that water move? How do you make sure that fluid doesn't do that? And like I said, yeah, I look at the horizontal. When I'm talking and training the operators and the pumpers I work with, I
Yeah.
think of it like a separator. I know, and basically the whole time you're producing that well, especially when we get into this optimization mode, that fluid is slugging continuously. One of the big reasons why guys with rod pumps and guys with ESPs and all this stuff are having trouble is because you get, it doesn't matter what we do, that's fluid is slugging and it's not consistent. You can't set a clock
Hmm.
by it. I mean,
Hmm.
the well does what it wants to do. So if I had an ESP, for example, and I'm slugging gas and I'm slugging liquid through it, and I'm hammering that ESP with fluid, and
Yep.
then I'm hammering it with gas, and I'm hammering, and that's one of the problems. So you need to control how that comes in. So that's one of the real challenges those guys have, and it doesn't really matter when we get down to these lower rates.
Hmm.
Uh, you just can't do anything about it. And the other thing is, we have no way that I've seen that's really working well yet, where we're able to increase that velocity down the horizontal, where we're able to
Sure.
move that fluid and keep it moving. So so we really we do an amazing job from the end of tubing to
Sure.
surface, but we cannot we really need to focus on that. So
Hmm.
this is kind of a long way around it, but truly the biggest problem I see is these wells have been liquid loading for months or years. It's
Hmm.
impacting the production, and it's not happening in the tubing, it's below the tubing
Right.
in
Right.
that transitional area and along that horizontal. But because we don't recognize it, we don't know we should do anything about it. So is that decline in that
Hmm.
well's production real? Is that,
Yeah.
should we
Yeah.
accept it?
Is it superficial because we've created a steeper decline because we're not unloading the well?
That's right.
You know, here's what I see so commonly done with our operators is if they are using gas flow rate for close, it's all based on a Turner Coleman or maybe some modified version of that. And you're right, that's all tubing based, and it's really effective for vertical wells. But on this horizontal section, what I'm trying to get to for the audience is like, okay, well, what do I do differently? And where my head's leading me, and tell me if this is correct, Clint. It's more of we used to strive for as low of off time as I could get. Like I just want that plunger to get to bottom, build up just enough pressure to get that thing to surface, and let's get it going. Let's lift that liquid out of that vertical and deliquefy. With horizontal, it's kind of leading me towards like off time isn't the variable you optimize towards to minimize because and hear me out like the off time maybe in some cases needs to be increased greatly. Let's just call it 2x because that downhole velocity needs to be higher, meaning you have to build higher pressure to get that full sweep of the liquid. So it's almost like you don't have to have more flowing time per day to get a higher daily gas and oil rate, right? Is that fair?
Um, yes, you're right on there. I mean,
Okay.
so I mean, basically, um, and kind of, I guess I'm kind of working my way towards that question. But if we have a continuous and steady flow going across that horizontal, right? So we're
Just
running,
stripping it.
stripping it, whether it's rod
Yeah.
pump or ESP or
Yeah.
what's happening. I mean, yeah, sure. At the end of tubing, the pressure's a little bit lower. We've got something
Sure.
happening, but it's still going to be so far. The rate going up that 2 3/8 tubing is going to be so far below what is required to make liquid move in the horizontal.
Sure.
It's still going to build up. It's still going to cause those problems. So, what tools do we have? What tools do we have to work in that horizontal with most of the ways we optimize? Right?
Yeah.
And really, the only tool that I found effective is the well's energy, own energy.
Yeah.
Basically, exactly what you're saying. Build up a little bit of energy, use that energy to create a slug, controlled slugging, trying to force the well
Hmm.
to move that fluid, trying to minimize the size of those water buildups or traps, right?
Sure.
Trying to keep it moving and keep it rolling. So
That's so counterintuitive to what we've been doing, though. Like, how do you get comfortable in just being like, yeah, the well used to be shut in for 30 minutes. let's shut it in for an hour and a half. Is it like how do you test that? What have you seen that works?
Well, I mean, the main thing with horizontal wells, and we talked a little bit about this, I think, in our last conversation, but there is a whole bunch of steps you got to go through to find, like, like the number one thing we should be doing is optimizing these wells 2 or 3 times, starting to look at optimization methods 2 or 3 times about what
Hmm.
your tubing critical rate is, right?
Okay.
Because we got to think about moving fluid in the bottom. So I'll tell a lot of guys, and we do this a lot in Canada and in a lot of different areas. We'll put a plunger lift in when the well is doing 2.5 million a day,
Hmm.
lifting 300 barrels a day. Now, is a plunger doing anything? Not particularly. The well can lift it on its own. But what's
Sure.
happening is we put this plunger in, we give it 1 or 2 cycles a day with an hour off. We let that plunger run to bottom. We build up that energy. The plunger sweeps that liquid out of the tubing, allows that end of
Hmm.
tubing pressure to get as low as possible, creates that good differential, and we get that big secondary rush. Then we let the well do its thing. Now,
Hmm.
most people, when they're looking at a well like that, they'd say right away, well, let's put a two-piece plunger in there, or let's do something that's very, very continuous. But it basically kind of pulls everything
Right.
down together, never creates that differential. And then as the wells move along and the plunger needs to do more work, you might actually have to go away from that 1 or 2 times a day
Hmm.
to, um, and it might not be an hour you need. It might be that we want to run a free cycle, or maybe it's a two-piece. I mean, that's this thing. There is no, I can't draw a chart and tell you at this rate do this, because every one of these wells are going to react different depending on how the fluid moves. But
Sure.
you might go from a solid plunger cycling it once or twice a day to a free cycle. And now what we're doing
Hmm.
is we're going to drop the plunger for 15 minutes, build up some energy, bring it to surface, drop it, and just cycle it continuously. Where we went from 23 hours or 22 hours a day of on production time, and that's all it was needed because the well had enough energy to keep that fluid moving with that little break. And then that production is higher. And guys will see it. Like, if I always say to guys, what happens when you shut your well in? Plant compressor goes on. When you bring that well back on, what does it do?
Yeah, it's happy.
Right, it's happy. Oh, it unloads a whole
Yeah.
bunch of fluid. It doesn't. Well,
Yeah.
why? Where it
Yeah.
didn't. Typically, that little bit of shut in just moves stuff and clears its throat.
That is so interesting you said that, Clint, because I've seen that in some of our customers' wells where, a shut in, it gives it 3 or 4 days. Let's just say a day shut in. It gives it 3 or 4 days of stably higher production than what it was before. Not like typical flush, on your vertical wells where you get a bump for 6 hours or a day and then it comes back to normal. I'm talking like sustained high and then it kind of falls pretty quickly back off. And I've actually seen that on some wells where they shut in and they come back so healthy,
Yeah.
right?
So if you look at that and you take, well, okay, flowing 4 days, for using your example, we're flowing 4 days at a 2 million a day. We're
Yeah.
making 8 million total gas, and I don't know, it's 800 barrels just for using number.
Hmm.
But for 3 days, if I'm flowing 2 million a day, I'm making or sorry, if I'm doing 8 and 4, and in those 3 days I'm flowing 3 million a
Sure.
day, I'm doing 9 million versus 8.
Yeah.
So you're
Right.
making more because your sustained production higher, and that oil comes in better, and you watch your water will be better. And man,
Yeah.
I can't stress this enough. Watching your water cut is key to understanding when
Okay.
the well is liquid loading. So anyway, so that goes back to how do we optimize these wells? And I
Yeah.
really tell all my guys, I mean, I'm a plunger lift guy, gas lift guy, right? That's what we do. But long before we need a plunger lift, that you can get benefit even from just shutting a well in. As I'll say
Hmm.
again, shut in for an hour a day, try it for 3 or 4 days, and compare it to the 3 or 4 days before. What does it do? Did we get a kick? Did,
Yeah.
and you can learn from that. Now, I'm not going to say this is guaranteed up against 100% of the wells, but
Sure.
a high
Sure.
percentage of the wells react very positively to that type of event.
Hmm.
Now, the benefit of running a plunger versus not running a plunger, even at these high rates, and people say, "Oh, we don't need them because we're above critical." what the plunger does that just flowing a well doesn't do is it sweeps the fluid much quicker. So you end up moving
Hmm.
all the fluid out of the tubing, and it allows you to get that end of tubing pressure a little lower. Also gives you things like wax control and other things that you can use.
Sure.
Now, obviously, you got to be careful for high speed impacts and things like that. But one of the interesting things to sidetrack a little bit is that high pressure wells typically have low velocity. I mean, even because they're flowing out, your tubing pressure is high, velocities are going to be lower. You don't see a lot of damage usually from high pressure wells. Where you see more damage in equipment is low pressure. Like nothing blows a
Interesting.
lubricator apart faster than a 30-pound well line pressure, because those
Yeah.
plungers can get such high velocity. So, and most of these big wells have all sorts of velocity control and things like that. So you can do stuff to ensure that you protect the equipment, get the advantage of sweeping cleaning paraffins out of the tubing, and you can take advantage of that, building up that energy and letting that well clean.
Hmm.
So way back in this well's curve, we've got that very sharp decline, and it kind of goes off and then
Yep.
lays out. Well, anywhere along there, and I'll send you a slide that we can add to this video after, but we can talk about. But anywhere along that decline, if we start doing something to move fluid with more effectively, you'll see
Hmm.
that the decline rates typically change. You may not get an increase, and this is another tough thing to talk about, guys. Is they're always looking for a production increase to justify it. The
Yeah.
number one thing you can do on horizontal wells is change the decline and flatten it out,
Right. Right. Great point there.
because
Yeah.
if if you're waiting, so if I put a plunger lift into a horizontal well and I get a big production increase, I've actually done a fairly poor job at optimizing. I've
Right.
waited.
All that curve before it.
That's
Yeah.
right. I've
Yeah.
waited, and so in a horizontal well, you put a plunger lift in. We're really going to affect, like, there's that big long curve
Hmm.
down, and then somewhere down here we get to, well, we're at a rate now where the tubing is loading. So we put a plunger lift in, and then you watch what the wells do. They'll typically, from the point you put the plunger in, it kind of goes straight across, and then
Sure.
it'll join up to what would be I would call the potential um, production curve. But if I'm
Right.
below that, so I wait, my critical rate is 500,000, and I wait till I'm at 200, and I put a plunger in, it'll bounce back up to that tubing line, like we'd see in a vertical well where you get that tick, and
Hmm.
it always goes back to the critical rate, or not, sorry, critical, but your decline, your natural decline.
Right. But you've missed so much to that point.
Right. But you don't go above that tubing point. So you can
Sure.
pop it back up and do a little kick. But if we're farther up that curve and we're trying to deal with the stuff below the tubing, we can actually change that very sharp decline. We can actually flatten it out a little bit. So now we can start to gain a little bit of production between where we're normally putting in plungers
Hmm.
and where we can change that decline. Now,
Right.
it's hard kind of explain that, but really it's surprising. And I've looked at wells and gone back and looked at wells that we've worked on several years ago, and we can see when we've done plunger lift. And I know that if I put a plunger lift in a horizontal well and it's doing 100 MCF, and I bump it up to 150, and then but from that point, instead of this 13% decline, it kind of levels
Yeah.
out. If I put that in at 300 or 400 MCF, I might not even get a bump, but what I'll see is that it'll just flatten out that decline, and it'll go on for years. And I mean, it's
Hmm.
still declining, but it's much less, and it's going to kind of run out to where it runs into, I think, the original potential.
Yeah. The original decline curve.
Yeah.
Yeah, and that makes sense to me. And I think I want to bring us back to the optimization piece because where my head was starting to move towards was, um, okay, so if we're not going to use critical rate to close a well, right? That's what you're saying is if we use critical rate, we're not effectively in a way deliquefying the horizontal because the rate down there is not high enough to bring the water. It's just stripping kind of the oil, the light ends. So, it,
Well, let me back that up. We can
all
still
right,
use
help me out.
critical rate to shut in, okay?
Sure.
Because the tubing is no longer effectively lifting fluid, so they want to stop
Right.
it. But when you want to optimize the horizontal, we need to create an environment that it can push the fluid into the tubing. So
Okay.
optimizing the horizontal gets back to, well, do we shut the well in and build up energy, right? So you can
Right.
end up 12 hours on, 12 hours off, kind of built in 10 cycles or 30 cycles,
Hmm.
2 cycles, depending on how the well builds. But by doing that, you're kind of, yes, you're shutting in on critical rate because the fluid.
So you're still shutting in on critical rate with the horizontals, but you're optimizing your off time differently. Go through that with me.
Right, because what we're trying to do is figure out what energy we need to make that fluid get into the tubing. So
Hmm.
if I was running a 2-piece plunger, I'm shutting in for 10 seconds, there's nothing going on. I don't care what I do, that fluid is going to sit there and churn, because if you're in a 4.5 inch piece of pipe below that tubing, you could have a critical rate of 3 or 4 million a day easy, and we're producing a
Hmm.
well at 500,000. Well, I don't care what you do. You can run that plunger up and down as much as you want. It's not lifting that fluid effectively, and any
Yeah.
fluid that it grabs is just going to be that top layer that it kind of sweeps along a little bit. Most of that fluid is just going to sit there. It's basically got to probably fill up to the point where it's creating an area small enough that it can
Yeah.
push that fluid, right?
Would be a good analogy here is if you have a 2 mile long horizontal, almost thinking it like about it like a conveyor belt, and you have like liquids towards the back end that will never advance towards the front, being the water elements, without like a proper surge or a proper kind of tidal wave to kind of push these things out of their slumps, or the sloughs. So would you almost say, like, if you think about that lateral as a conveyor belt and you're just kind of advancing this water forward and you really kind of want it to be staged at the bottom of the tubing, prepared, ready to go up, you can't necessarily you can have a backup on this conveyor belt at these sloughs because you're not, or if you don't adjust your off time, appropriately, having a little bit longer to advance it. So I guess I'm trying to bring it back to an analogy for the audience. Is like, is a conveyor belt fair?
Um, yeah, I don't know.
Because it's a
Yeah,
complicated topic.
it's I don't know if it's to me it's more. This is how my mind thinks of it, which may be
Okay,
completely wrong. And there's some brilliant guys out there.
I know mine
Yeah,
is. So,
so, but I look at it this way: we shut the well in. It's all that liquid that's churned and it kind of relaxes and
hmm,
settles down. Everything gets, and we fill in all these low spots or whatever, and then
yeah,
and then when we bring that well on, of course, that flow is able to basically, it creates that starts that wave, and that's what I see as a wave, and it just basically, maybe it does push that or
hmm,
first 100 low spots or whatever, a
sure,
slug along, like you're saying, like a conveyor belt. But it's, I just see it kind of pushing and carrying it on, and you just kind of hop it,
hmm,
maybe conveyor belt hopping it or whatever, and you're trying
sure.
to make sure you keep getting it there, and then
You want to advance it.
the final stage is how do we get around that transitional? The hardest in that whole well to get fluid around is the
Hmm.
transitional. So,
Let's talk through that. How do you get through the transitional?
well, you basically got to have an instantaneous rate high enough and a slug that it's able to handle, which is key, right? So
Hmm.
that's where we don't want to have 100% water. We want to make sure that when we're bringing the fluid in, we're keeping the proper percentage of water, oil. If the well produces 8% or 10% or whatever, try to keep that as close as possible. And basically, when you bring that well on, we're getting that nice end of tubing pressure as low as possible, and we can create that short term, instantaneous high rate that's going to let us
Sure.
kick that fluid around the corner and carry it. Now, in all this discussion, and we can talk a little bit about it, but end of tubing position is so critical. Like if I
Mm.
got my end of tubing sitting at the vertical at kickoff or something, I don't know what it's going to take. The only way you're going to get fluid there
What's going to get it
is,
there, right? Because you got a 4.5 inch down there,
yeah,
which is a bigger piece of pipe. How are you going to get it there?
that's right. I mean,
Yeah.
you just can't probably even get the velocity up the tubing
Yep.
to even get to the critical rate. I don't care what you do, compression, do whatever. You just
Sure.
can't. It won't happen. So, and if we jam that tubing, because lots of guys say, oh well, let's just jam that tubing right down into the heel and get her at 90 degrees.
Let's go 85.
Yeah, that's right. Well, that's also a problem because
Yeah.
and there's not a lot of advantage, and I've looked at a lot. I've talked to, I don't know if, do you know Dr. Nagu? He does a
I
lot
do
of
not
these
know.
modeling. Anyways, he's a very interesting guy, and he models this stuff, and he blows my mind. He's so far beyond what I.
I think I follow him on LinkedIn actually.
Yeah,
Yeah.
but he's got some great modeling and stuff, and that looks at that. But and I've talked to him several times, but there's a point where when that tubing goes in, and through trial and error, not through any wizardry with math, I found that it's about 70 degrees from vertical.
Okay.
If we landed that, we get really good, like the well's able to push that fluid to end of tubing,
Okay.
and then the small bore tubing actually can carry that fluid much easier um, through, like, from 70 degrees back the horizontal. And of course, from that 20 degrees from, so I'm 70 degrees from vertical, 20 degrees
Yep.
from horizontal, but kind of from that tubing entrance to probably, I don't know, six, maybe 70, say around that 20 degrees. So that would, yeah, 20 degrees from
Hmm.
vertical is really the hard area. But if it's going through that tubing, you can actually carry it through there.
Yeah.
And
And that's a topic I think I want to clarify is like the reason it's easier to go through a smaller ID, diameter is like you have a smaller area to have to like push up. If you're in a wider tubing, or sorry, a wider casing, 4.5, 7, 7.5, whatever it is, it's just harder. Think about a straw. Like it's easy to push fluid through a straw, just like very little effort. But if you have something this wide, 4.5 inches to do it, it takes a lot more effort to lift it because of that surface area. So the smaller the pipe, think about like a velocity string. You see some people put old coil tubing in a well because you can get it's easier to lift through a smaller ID. I guess I just want to make that point clear on the why it's so critical to have that tubing so low at 70 degrees rather than at vertical, is really because the velocity is easier to achieve at that point, right?
yeah,
Physics.
70 degrees is where I've seen it works better. No,
Okay.
72 the perfect, or 60. I don't know. 70 degrees is my. Let's just set it.
It's not 80 and it's not 60.
That's right. And if you go down to say 90 degrees, one of the biggest problems you have is now we got this straw, using your analogy,
Hmm.
sitting down and then in that heel. And every time that well shuts in, what all that fluid that's been churned up and gasified and go, what do you think it does? Right? It all
Mm.
collapses down, and now it's sitting at the end of that tubing. And now I've got a 4.5 inch piece of pipe with, I don't know, 1,000 feet of fluid sitting around it. So when I go to bring
Yeah.
that well back on, I've got,
Interesting.
right, basically I've got this pressure pushing the fluid. Well, it's got to push all that fluid out of the way before gas
That's so
can
much.
enter the tubing.
Yeah.
So all of a sudden, I shut the well in for 15 minutes, and there's another piece we can talk about how fluid gets hung up above the tubing.
Hmm.
But I've got all this fluid. The pressure starts pushing that fluid into the tubing, and with a 2 3/8 to 4.5, it's basically 4 to 1. So I could have,
Wow.
I don't know, three.
There's no way you're lifting all that liquid up to
Right.
surface. I mean, that's just too
And,
much.
and lots of people, I've seen this, they'll say, well, if I shut in the well more than 10 minutes, I can't get it to come back on. The well's still producing fluid and it's flooding out. No, that's, I mean, I can't say 100%, but I can tell you the majority of the time, it's just action of having the tubing in at the heel. All this
Yeah.
fluid is collapsed around, and when you try to bring it on, basically you get a big slug of fluid that overbalances, and the well just doesn't have the energy to drive it up.
Hmm.
But when you're sitting at 70 degrees, you have fluid entry and you get gas entry. So you
Yeah.
string that liquid out and you put gas in it, so you get the advantages. As that liquid and gas are coming up, you're getting expansion. If I
Hmm.
drive a 500-foot column of liquid up that tubing, it's pretty darn heavy. So very
Yeah,
hard to
absolutely.
restart. So I've had guys say, well, if we're doing Gapple, we can go a little deeper. Sure, you've got that energy to kick it around and get it
Yeah,
going again. It may, but I never really have seen a great advantage going past 70 degrees. You
sure.
know, it's there may be some things a guy can try, but I don't have any empirical data or
Yeah.
experience for that. But 70 has worked amazing.
So I want to summarize that, and I do want to hit the element you said about like the liquid flowing behind and past the tubing. So yeah, so what I'm taking away here is if you go 90, if you go really deep, you're going to be dealing with a lot of liquid to push up each cycle. So probably going to require you to either short cycle and just not get to bottom, and um, that's the only way you're going to run your plunger, but it's not really effective, or it's going to be really really long build times. just to have to force a huge liquid column out of there. The other piece is the having it at 40 degrees or 30 or higher than that uh, is ineffective because of how much energy is required to lift that liquid and to lift the liquid through that 4.5 to the 2 3/8 to get it to surface. So your sweet spot is really at that 70, or plus or minus 5, because what you're doing is you're allowing that tubing to get low enough, and for the benefits of having that velocity, lower velocity required, at 70 degrees, so you don't have to push the fluid as far, but it's not far enough down to where it's absorbing all this liquid, and it's a huge slug each time. Is that kind of a good summary there, Clint?
100%. Yeah. Yeah. I mean,
Sweet.
otherwise it's just a straw in a big cup, and
Yeah.
try and blow that water out of that cup with a straw sticking in the bottom and see
Yeah.
how hard it is, right? So
Yep.
yeah, definitely that, and that's exactly it. Now, yeah, and getting so talking about the fluid, so around the tubing,
Yep.
it another thing to think about, because remember this well is constantly slugging. It's sending these big slugs, and they're carrying on,
Hmm.
and when that fluid comes scooting along, and then it comes hammering into the end of the tubing, there's a like basically that slug of fluid. There'll be a low pressure in front because the energy is going up the tubing, so the pressure is dropped around the tubing, and you've got a high pressure or a higher energy area behind it
Surge. Yep.
pushing it. So it slams into the end of that tubing. Only a percentage of that fluid, I don't know what it is, 40% of the fluid goes up
Hmm.
the tubing. And the other, because there's a low pressure, basically it's squeezed up and held above the tubing until that energy behind it kind of drops, and
Yeah.
then that liquid can start to fall back. Now, if you asked me when I first started working with horizontal wells if this was possible to have a flowing well with liquid above the end of tubing, because my vertical experience says no, can't happen. I have, and we've looked at many wells where we've done continuous monitoring on the casing side,
Hmm.
and we see it in basically every well we check. If that well is
Wow.
lifting fluid, it's carrying a fluid column, and it bounces up and down above the end of tubing, and
Mm.
it's this action of liquid slugging in, getting held up, then as the fluid drops back out, and pressure, and it's because you're getting the,
Hmm.
2 miles away, I've got a whole bunch of pressure pushing fluid, and there's big energy, and then that energy pushes and holds it, and then as that energy is dropping, as
Interesting.
it's pushing liquid up, there's another slug coming. So and there's another. So and it's just basically, man, we can track it, and it's it was surprising, but it really was another key thing, and it really made me understand. Well, why are we having all these troubles? Because trying to run a plunger lift on a horizontal well in the beginning was, man, everything I do that worked before kicked my butt. you know?
Yeah. Yeah. Absolutely.
I remember the very first well that we really got on, and I watched that casing pressure, and it's going down, it's going down, it's going down. Man, we're doing an awesome job, and it kept dropping. The well's flowing along, and all of a sudden it just went doop and died.
Yep. Whoop, that curve. I've seen that before. It's just, yep. It's the flow rate's doing its thing. Actually, flow rate's doing its thing, and then it just like takes a turn, and you're just like, wow. Within 5 cycles, that thing was loaded.
And you go, well, what the heck? Everything. I mean,
Yeah.
right? But then you got to remember that the reason that pressure on the casing is dropping is because here's my end of tubing. Well, here's my energy. So
Hmm.
I'm what's happening is I'm actually just leaving a whole bunch of crap in between the well and not moving it, and I'm holding that energy back. So a lot of
Hmm.
that nice, and I've seen it go over a month, where you can start a plunger lift on a two piece and watch that casing go do 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 for a month, and it hits
Yep.
the wall
Yep.
and it dies. You go
Yep.
back out there the next morning, hit the button, and away it goes again. But that same well, if we gave it
I've seen that.
15 minutes off between cycles
Yeah.
and 15 or 20 minutes on, it'll run as smooth as can be, produce more well liquid,
Sure.
produce more gas, and because we're not letting that fluid
Hmm.
slowly build up. And I didn't realize it at the time when I saw that, and it was a real head scratcher.
Yeah.
Um,
So that's something for people to look for, right? Is if they're seeing, we'll call it a week, 2 weeks of pretty consistent production, arrivals, and such, and then a really quick fade away to where the plunger hits a non-arrival. You can see it on the flow rates dropping and such. It is a pretty good indicator that your well is in need of some sort of off time, and the sacrifice of the off time is worth it. Not only because of the build up time required to get it back, right? those 4, 6, 8 hours of shut in. But really because like you can still have continuous steady production and avoid that event, the non-arrival event, by just giving it a little bit of love to build, right? Yeah,
Yeah, because we're not gonna let that fluid build up in the horizontal. We're just
sure.
tickling it over to the tubing and pushing it out, which is allowing our formation to, it's not having to fight all
Hmm.
that liquid that it is pushing along the horizontal. So
Okay. Yeah, this has been really interesting for me just to understand that you do because what I had originally I ideated was like, man, do we need to have a higher flow rate shut in at surface? Sounds like we don't because I was thinking, man, if the critical rate downhole, it's 15 or 1.5 million to move all the liquid. That means it has to be what it is and shut it at the surface. Doesn't sound like that's the case because really we're dealing with the tubing, and that's why we shut it in with critical rate. Second piece being, off time, super super critical to maybe test and watch behavior, right? To see, well, my well is having some loading issues. Like, what if I just test this out? I'm going to go from 20 minutes off to 30 or 40. Just see how it's building. See if you're getting more liquid. See if you're getting more steady production. But play with it and to see if the behavior changes. The concept you threw out of the 70 degrees. I mean, that's probably one of the first times I'm really hearing about like an ideal selection location for plunger lift. Like super super interesting. And then I think for me, just understanding that lateral is more of a separator is so useful because then you really think of it as like, well, that makes sense that my oil kind of gets stripped away first. And then I'm left with a lower water cut, right? Because I'm basically pulling all of my oil up. And when you're seeing that trend of oil and water, or sorry, oil production probably staying the same and water production going down, probably having some loading issues downhole. Like, question yourself, where did the water go? Why is the water gone? Right?
yeah,
Probably downhole sitting there, right?
yeah.
So I think that those are some really big takeaways for me. What else do you think would be something useful to share with the audience before we kind of wrap it up on liquid loading and the horizontals? You shared a lot here today. Any other like key messages the audience can take?
Well, the key, the most important. So, from a production engineer manager, is
Yeah.
don't get stuck on critical rate and tubing. Understand the
Mm-hmm.
full
Okay.
well bore, and and if you not understand, but try to learn how your well bore works. Start doing things early. I like just cycle the
Mm-hmm.
well for a few days, an hour off a day, and see what it does. What do you learn? You don't even have to put a plunger lift in it. Just tell your skater to shut off 1 hour a day and see what it does. I mean,
Yeah.
it may go south. I'm not going to tell you, but maybe there's a completion issue. But at
Sure.
least learn a little bit about it and try to understand where your problems are, and and you got to think. Plunger lift and horizontal wells. You're not just dealing with the tubing. The tubing is easy. We can
Mm-hmm.
we can industry can deal with the tubing problems
Yes.
100 ways to Sunday. It's
Yep.
understanding how to deal with the problems below the tubing in that horizontal, and you really got to think about it. And if you can understand, think about it in this. There's this long separator, and there's this fluid movement, and then there's these huge rates that I don't think people realize what it really takes to
Mm-hmm.
move fluid. It really can help you when you're standing at that wellhead and something happens, and if you can picture that, it really makes a big difference in understanding
Yeah.
of why you do something. Because it is counterintuitive to say, well, shut in a well that's doing 2 million a day, right?
Yeah.
But
Yeah.
but I can tell you, we worked on these were in a Montney, did a whole bunch of work, and what was interesting was as we started to do this and we started to add some off time, and these wells would run two piece and all. We started playing
Mm-hmm.
around with them. We could see a production trend, and the production's going along. We stabilized and run along, and a month or two into the production, all of a sudden we just had these like a bump.
Hmm.
And now, at first, talking to the production, oh, it must have been a sand bridge, or must have been this, must have been that. But we would see it in the Montney quite often in this one area. And what we actually came out with in the end was we actually think that there was fractures that were probably completely saturated with water or fluid,
Sure.
and
Sure.
basically it shut off a bunch of that formation.
Yeah, it's like you had a plug back there,
Right,
just
right.
sitting there plugging it off.
It's
Yeah.
very hard to move that liquid out of the rock once it's there.
Right, right, right.
By cycling this and kind of what we were doing was we were making that from that point where the fractures were saturated, we were dropping the
Hmm.
pressure in front of them, allowing enough differential to break that fluid tension to allow the formation to start pushing the fluid out of the way. Now, how did that fluid get there? Probably what's happened is it was sitting there and then the well got shut in for a while and then everything pressured up
Yeah.
and it just squeezed the fluid in.
I wonder if it could have been like a toe down or something. Like if it's at the edge of the well and it was a toe down and you had that liquid kind of sitting there.
It
I don't know.
I can tell you this, that there was toe down and toe up. There was there
Ah,
was a mix because, depending on which way those wells were taken off the
yeah,
map,
yeah.
and they would do it. We could see it in multiple. There was no uh, discernible trend on toe up or toe down
Okay.
that I could say, but there may be, but we just don't have enough
Yeah.
evidence to say, oh yeah, well, it happens 70% more in a toe down. That
So you're unlocking part of your reservoir potentially
Yeah,
that is in a way plugged off by kind of the saturation of water because it's not being deliquified efficiently because we're basically leaving a ton of water down here in our horizontals and we're just stripping
right, right,
oil.
and across that horizontal, you've got 1,000 little peaks and valleys, and we got water in every one of those.
Hmm.
We could have that into tubing down to 300 psi. But when you go through every one of those little tiny valleys and you calculate it out, you could have 7, 8, 900 psi sitting back 2/3 of the way back.
Yes.
And you, no matter what you do, you're never really getting it low enough to kind of clear that out again. And
Yeah.
we didn't see it things like the Duvernay, West Duvernay, or some of these deeper formations. I don't, if it happened, we're not sure, but it was really interesting that we saw that in these Montneys that um, and they were more water, gas, less oil. So that maybe that has
Hmm.
something to do with it. But it was just an interesting observation that we got. So,
Yeah.
so
I want to add on to that. So when I was in Prudhoe, we would have these coil sidetracks, like, we'll call it 3,000 feet or so out of a vertical well. And they were 2 3/8 ID for the horizontal. So pretty narrow, right? So you pretty quickly get velocity, pressure restricted. So all of your production is really going to be coming from that heel. Anything close to the heel is really where you're producing most of the fluid from. And then the further you get back, you don't have enough pressure drop to really bring in. So we found like, man, like the edge, we would do these production profile logs and figure out like, wow, the toe of this well is basically not contributing because we can't drop the pressure low enough to really get it to draw down and give us fluid and gas. So I think that theory is pretty sound. The question is, how do you know that on your decline when you only seen what you know? Like, is there something there? Who knows? But I guess to be safe, really, let's get the horizontal fully unloaded. Let's get some water out of there, and let's do it through some off-time builds and some critical gas rate shutoffs to the tubing. Do some testing, play around with those off times. But I think what you've shared with me here today really makes me question a lot of the ways I think I've heard the industry is really doing their horizontal plunger lift management, and I think there's some really sound theories behind it. Right?
yeah, and it's not the silver bullet. It's not going to be the
Sure.
savior to everyone.
Nothing here is Clint, right? I mean, every well is its own character, right?
But if you're trying to understand your field and your formation, you've got to try some stuff. And I think they wait too long. And
Mm-hmm.
it's this is a truth. The longer you wait to work in optimization, the harder it is to get results.
Fair.
You
Very
can't,
fair.
you know. And the other thing with horizontal is every MCF of gas that I produce out of that well that I'm not using to lift the liquid that came in with it is liquid I'm going to have a hell of a time getting out later.
Mm-hmm.
And that's the other thing. Like, you getting back to when you see the flow guys run these wells continuously and they're not lifting much fluid, but they know that their gas liquid ratios are kind of changing and things are going on. Well, are they really changing, or are we just not moving it as good, or what's going on? So that off time, lots of times you'll see you'll pop them back up. You'll be able to produce a lot of
Mm-hmm.
liquid. And things like that. So
Okay.
so yeah, it's long before you get to critical rate. The number one thing is look at your well, think
Good
about
point.
what's there, and try something. Or just
That's
think of the
good.
last time the compressor went down. You brought the well back on.
Yeah, just look at your last shut-in. Was that good or bad?
Yeah, what
Is that that's really good. Hey, we should actually note that. Yeah, look at your last shut-in, multi-day, single-day shut-in, and how did that well respond? Did it respond in a way that surprised you? That it responded in a way where you did get a lot more water production than you would have expected for just a single-day shut-in? Because that may be enough to question, well, are you operating it the way it should be for deliquifying the horizontal? Yeah, that's a good tester there, Clint.
and it's kind of funny because you talk to guys and they expect that kick. Oh, that's what they do.
Mm-hmm.
But it never
Sure,
kind of
sure.
gets, well, if I got it once, what happens if I do it?
Why?
Yeah, well,
Yeah,
well, it builds up and it creates a bunch of energy and your
yeah,
well bore and the horizontal, and we get all this. So,
yeah.
but there could be something there that allows them to do it
Mm-hmm.
artificially, basically.
Yeah, structured, and there's a
Structure.
process behind it. It's every hour. It's on the RTU, right?
Right.
That's it. It's great. It's
Yeah,
great.
and you may not need plungers. You may not. I mean, you may be
Mm-hmm.
well early in the well's life. It makes a difference.
Sure.
And then you may look at adding plungers still at 2 or 3 times. For other
Sure.
reasons, mechanical reasons for wax and other things. Even if you're using gas lift, and you know what happens if there may be advantages by shutting and building up and going on. I mean, it can be hard on valves if you're cycling them open and
Mm-hmm.
close all the time. But there's other things, high pressure and gas. So there's lots of things to think about, but it's just moving away from the tubing. Move away from the end of the
Sure.
tubing as being your mark in the sand where you're going to do something.
Your performance. That's great.
Yeah.
Well, great. I'll throw a quick plug in here for Kaizen. Yeah, if anyone's looking for gas lift and plunger lift solutions, Clint's got a business and he knows his shit. So worth talking to, worth getting some training from, worth using their materials. They've got some great plunger lift products and some pretty interesting gas lift hole or tubing. Hole and tubing detections, but I think would be a really cool podcast for us to talk about
Yeah.
next. Is maybe some gas lift
Yeah.
insights you've shared there, Clint.
Talk about
Yeah,
well tracer and CO2.
yeah,
Some of the
that'd
other
be really
things that we're
interesting.
figuring out and working on. And another real interesting one that we should talk about, I think, on the gas lift is the performance between 1 inch and inch and a half valves. And
Okay.
because uh, there's a real big opportunity increasing performance between the two.
Awesome.
And it comes right back to completion. I mean, if you're running 4.5 inch casing, it's pretty tough to fit inch and a half valves in there, but it
Mm-hmm.
has a huge impact on getting to the bottom, valve performance, pressure
Mm-hmm.
drops, getting that single point versus multi-point. Just in the performance, it's all mechanical in the valve and bigger cross
Mm-hmm.
sectional area. So that would be an interesting one, I think, as well,
Okay.
because we learned a lot because of the technology that we've got, the AppSmith side that I didn't
Yeah.
realize. I mean, I'm a plunger lift guy through and through, and a budgeting gas lift guy. I've got my brother, who's really the gas lift guy, is the
Sure.
real wizard behind it. But yeah, there's lots of really good things to talk about there. So
Yeah, that's what we're here to do. We're here to share with you all the technology kind of going on in the oil and gas operations world and how it can help you in operating your field better. So, I want to thank Clint for joining the podcast today, and he'll be on here probably in another 2 or 3 weeks because you can't get enough of this guy, right? He's got all the knowledge you want. So, appreciate the time here, Clint. Really, really good time.
and just throw this out. I mean, if we've got people out there that are listening to this and they got thoughts and questions,
Great point.
let's throw them up there because I love talking about real life issues,
Good.
and I like hearing from people, and even people disagree.
Yeah.
I'm not infallible. I can tell you that. I make mistakes, so it's good to learn together as a.
So what Clint's saying is go talk shit to him on LinkedIn. Clint Mason challenges thoughts there. That's what he's saying. No, I'm joking. We would love to get the feedback.
Yeah,
Love to hear all the suggestions and yeah, any real world examples. That'd be really interesting. If someone wants to send us a screenshot or a plunger well, give us some history on it. Maybe we can dissect it here, or that could be a gas lift well. So we can do that live and get some insight. So do reach out to Clint and I, and we'll see what we can do there.
you bet. Well, as always,
Awesome.
it's been a pleasure. I always enjoy this, and yeah, it was great, and I look forward to catching up again, and when you have time.
All right. We'll see you soon, Clint.
All right, take care, everyone.
See you.